So now we'll see stack. So stack is a list of elements in which an element may be inserted or deleted at one end, which is known as top of the stack. It's called LIFO. LIFO means last in first out. So we call a stack representation as last in first out LIFO because whatever is placed at the last will be removed at first. So let's say a stack of books, a stack of plates. So whatever book is placed at the top of the stack, which is the last one, will be removed first. So that's why it's called LIFO, last in first out. Then if you see, we'll see an example here. Let's say we have this stack of books here, triple A, triple B, triple C, triple D, triple E. So triple E is called the top of this stack. If we remove triple E, then the next top will be triple D. So because we placed triple E at last of this stack, because first it was placed triple A, then on the top of triple A it was triple B, then similarly triple C, triple D, and then triple E. So here you'll see examples. So we call we define as push, pop, and top. These are the three terms we use for stack representation. So let's say we have this a stack of books, and the top of the last one is the top of this stack. So if we remove this last one from the top, we will pop it. So it's called pop. So we use this function pop. So we are popping this from the top, and when we are adding and placing another book on the top, we are pushing. So we use push. So push, top, and pop, these are the three terms we have to remember for stack representation. Next we have queue. So a queue is a linear list of elements in which insertion can be done at one end, which is known as front, and deletion can be done, which is known as rear. It is called FIFO. FIFO means first in first out. So whichever or whoever comes first will go first, like that. So we'll see here example. So these are two operations. Queue perform these two operations. We can add a new element in the queue, and we can remove an element in the queue. So these are insertion and deletion. So if you see this example, this is the representation of queue. So let's say we have 75 comes first in this queue, and then 65, then 55. So which one will go first? 75 will go first. It's just like a queue or a line in a bank counter, or in a bus counter. So when people are standing in a queue, whoever comes first will go into the bus first. So this is how it works. So if you look at this image, the queue has two pointers, front and rear. The front points to the first element, the one that will be dequeued first, while rear points to the last element, the most recently inqueued one. Now here the nodes are linked using pointers, which with each node containing a value like 10, 20, 30. So a pointer to the next node, which is represented by a memory address, which is highlighted in red. So if we say the first node contains the value 10 and its pointer 0 into 10 points to the address of the next node, then node 2, the second node, contains the value 20 and points to the next node at address 0 into 200. Then the third node contains the value 30, and since it's the last node, it points to null, indicating the end of the queue. So the front pointer points to the first node 0 into 50, and the rear pointer points to the last node 0 into 200, allowing us to efficiently add to the rear and remove from the front. So how can we do the operations in a linked queue, like in queue and dequeue? These are the two steps we do. In queue means insertion and dequeue means removal. So to add a new element, we allocate a new node at a specific memory address, link the current rear node to it, and update the rear pointer to point to the new node. And then to remove an element, we move the front pointer to the next node in the sequence, effectively removing the first element from the queue. So we will also learn more about these things. Okay, so now let's look at linked list. A linked list is a linear collection of data elements. It has two parts. Part 1 is info and other is link part. Info part gives information and link part is address of next node. So we do these 4 operations performed on linked list: traversing, searching, insertion, and deletion. So we already looked about and discussed about this type of operation before. So these 4 operations are performed on linked list specifically. So we'll now look at an example here. This is an example of a linked list. So these are the values. So the first node has value 2 and the address is pointing to the next node, and then the second one value is 4 and then the address is pointing to the next node. So sequentially it does, and the last one pointing to null. Okay, so here we will now move forward to non-linear one. Tree and graph are non-linear data structure. So in computer science, a tree is widely used data structure that emulates a hierarchical tree structure with a set of linked nodes. And then here we'll see these are the operations we can do on tree: insertion and deletion, and then searching. So these 3 operations we can do on tree. So we'll also learn more about these things later. Okay, so here is a graph of a tree. So I think it's not very clear. The picture is not very clear. The alphabets are not very clear. So anyway, so the first one, the top node, is the parent of the total tree, and then all these nodes are child of this parent. And then if you see here on the left side, that one is the parent of the of these 2 child. So similarly here we have lot of child and lot of parent, but the it's like a family tree. So we can add or remove So we'll learn more about these things later. Okay, now graph. So a graph data structure may also associate to each edge some edge value, such as a symbolic label or a numeric attribute. So a graph is specifically consists of nodes which is connected. It could be directional or indirectional. It depends on the data, or it depends on the value. So these are the three operation we can do on graph. Similarly, like we did on tree, we can also do searching, insertion, and deletion. Okay, so here is an example graph. This is a graph of graph. So this is a diagram of a graph. So if you see, we have 1 2 3 4 5 6 nodes. These are denoted as A, B, C, D, E, F, and these are connected, but it's not directional. So there is no direction in this graph. So all these edges, so these are the line which is which connects two nodes are called edge. So these edges can be directional or non-directional. So there is no direction in this one. So this is how graph looks. Okay, so now we'll move forward to an important topic, algorithms, which are essential components of computer science and programming. An algorithm is a well-defined set of instructions that is used to solve a particular problem. It tells us how to perform a specific task step by step. In data structure, algorithms are fundamental for performing operations such as searching, sorting, inserting, or deleting data efficiently. Now let's look at an example of a simple algorithm for finding the location of the largest element in an array, called the largest item algorithm. The algorithm is designed as follows. First, we'll do initialization. Start by setting k equal to 1. This variable will iterate over the elements of the array. Then lock equal to lock means location equal to 1. This keeps track of the current location of the largest element found so far. Then max is the maximum equal to data 1. Assume the first element is the largest initially. Then loop through the array. The while loop runs until k is less than or equal to n. This loop will go through each element to check if there is a value larger than max. Then update max value. If max is less than data k, then update. So if max less than data k, then update max to data k and set location to k. This means we have found a new largest value at position k. Then we will increment the index. Increase k by 1 to move to the next element. Then output the result. Once the loop completes, write the values of max and location to indicate the largest value found and its position in the array. And then finally exit the process. So this simple algorithm has a time complexity of 0n. That means that it must iterate over all n elements in the worst case to find the maximum. It serves as a foundational example of how algorithms help us systematically solve computational problems in a clear logical manner. Okay, next let's discuss a critical aspects of algorithm, their complexity. When we design algorithms, it's important not to just solve problem, but to do so efficiently. The complexity of an algorithm helps us determine how well it performs with different sizes of input data. The complexity of an algorithm often represented by a function fn which provides an estimate of the running time and or storage space needed as a function of the size n of the input data. So this helps us understand the resources like primarily time and space that our algorithm will require. So these are two main types of complexity we are concerned with: time complexity and space complexity. So time complexity represents the amount of time taken by an algorithm to run as a function of the input size. This is often expressed using big O notation, which provides an upper bound on the running time. For example, if an algorithm runs in big O n times, this means the time taken grows linearly with the size of the input. Understanding time complexity allows us to estimate how scalable an algorithm is and compare the efficiency of different approaches. Then we have space complexity. Space complexity represents the amount of memory required by an algorithm to run in terms of the input size. This includes both the space taken by the input data and any auxiliary storage used by the algorithm. Some algorithms may require significant additional space to process data, which is why balancing memory usage with performance is essential. Now, these two measures, time and space complexity, help us make informed decisions about which algorithms to use for different problems, particularly when considering limited computational resources. For example, while some algorithms may be faster, they might also require a lot of memory, making them impractical for certain environments. So let's now dive into big O notation, which is one of the most important concepts in analyzing the performance of algorithm. Big O notation provides a way to describe the upper bound on the growth rate of a function, typically used to express the time complexity or space complexity of an algorithm. In other words, it tells us how the runtime or memory requirements of an algorithm grow as the size of the input increases. Formally, we say that a function fn is big O gn if there are positive constants c and n0 such that, if you look at this function here, fn less than equal to c dot g n for all n greater than equal to n0. This means that gn acts as an upper bound for fn for sufficiently large values of n. Essentially, it ensures that fn grows no faster than a constant multiple of gn. So these are the example. In first example, we'll see fn equal to 3n plus 1. Now, in this case, we can see that fn is bounded by bounded by 5n for n greater than equal to 1. So we write fn equal to big O n. Here the linear term 3n dominates such n grows larger. Here the linear term 3n dominates as n grows larger and the constant 2 becomes insignificant. So if you see the example 2, here we have fn equal to 3n square minus 2. Here fn is less than 3n square for n greater than equal to 1. Thus, we can write fn equal to big O n square. The quadratic term 3n square dominates as n grows larger, while the constant minus 2 becomes irrelevant for large values of n. Now, why big O notation matters? It allows us to classify algorithms based on their growth rates and scalability. By, by understanding the upper bound of an algorithm's complexity, we can estimate its behavior for large inputs, allowing us to compare different algorithms and choose the most efficient one for our needs. For example, if one algorithm has big O n complexity and another has big O n squared, the first algorithm is more efficient for large input sizes since it grows more slowly. Now, as we continue our discussion of asymptotic notation, it's important to understand some of the rules that help us work with these notations more effectively. These rules provide insight into how we combine or simplify expressions involving big O, which is useful for understanding the efficiency of algorithms when they involve multiple components. So here, if you look at the rule 1, combining functions. In rule 1, it's suppose we have two functions, a and b. Then if you look at these two functions, then the complexity of adding these two functions is given by the okay, the third one. Okay, so this means that the combined complexity is dominated by the larger of the two functions. For example, if so it's very difficult when it's online class to just classify those things, these equations. Okay, so if, for example, if g underscore a n is big O n square and g b n is O big O n, then f a n plus f b n will be big O n square. So if we do multiplication, the complexity when multiplying the two function is f a n dot f b n equal to big O g a n dot gbn, which is the last function here in rule 1. So if you multiply two functions, the resulting complexity is the product of their individual complexities. For example, if an is big O n and if bn is big O log n, then their product is big O n log n. This is the rule 1. Now on rule 2, this is polynomial functions. If fn is a polynomial of degree k, then fn equal to big O minus nk. So I think it's big O, not minus, some typo maybe. Okay, so this means that for a polynomial function like fn equal to 2n cube plus 5n square plus 7, this is a polynomial function. The highest degree term n cube in this case dominates as n grows larger. So fn is theta. Oh, that's theta. That was theta. Okay, so so fn is theta n cube. The theta notation here indicates a tight bound, meaning the function grows asymptotically at the same rate as n to the power k. Then third one is logarithmic function. Then rule 3, for any constant k, we have log to the power k n equal to big O n. This means that logarithmic functions, even when raised to a power, grow much more slowly than linear functions. As n grows larger, any logarithmic function is eventually dominated by a linear function. This rule tells us, in terms of big O, a logarithmic term, even raised to a constant power, will never grow faster than n. So, why these rules matter? Understanding these rules help when dealing with the complexity of algorithms that combine multiple steps or involve different operations. By applying these rules, we can simplify and determine the overall complexity of an algorithm, which make it easier to evaluate its efficiency and scalability. Now we'll see a chart, growth rates chart. To understand the efficiency of algorithms, we need to consider their growth rates. Growth rates describe how the resource requirements, like time or memory, of an algorithm scale as the size of the input increases. So let's discuss some of the most common growth rates, starting from the slowest to the fastest. First is constant. This is the most efficient complexity, meaning the operation takes a constant time regardless of the input size. Accessing an element in an array by index is a common example of constant time complexity. Second is logarithmic. Log n. If we say log n, the growth rate is big O log n. Logarithmic complexity grows very slowly, making it highly efficient for larger inputs. Binary search is a classic example of an algorithm with logarithmic time complexity, where the problem size reduces by half at each step. Then we have log squared. Growth rate is big O log square n. This is slightly more complex than big O log n, but still significantly more efficient than linear or quadratic growth rates. Then we have linear. Growth rate is big O n. Linear complexity means the time required grows directly proportional to the input size. Examples include simple for loops that iterate through all elements. Then we have linear arithmetic, like the growth rate is n log n. Algorithms with this complexity, such as merge sort or heap sort, these are efficient for sorting large data sets. Then we have quadratic. Growth rate is n square, which means big O n square. So all these growth rates we have to include big O. So these are called big O n square, big O n log n, these like that. So quadratic complexity means the time grows proportionally to the square of the input size. This is typical for algorithms involving nested loops, such as the basic implementation of bubble sort. Then we have cubic, where we have growth rate n cube. With cubic complexity, the time requirement grows with the cube of the input size. Then we have exponential, to the power n. So exponential growth is extremely fast and becomes impractical for even moderately large inputs. Algorithms with exponential time complexity, such as those solving certain combinatorial problems via brute force, are generally inefficient and only used for small input size.